So this is the second half of Lab 2 for ST2, where we're looking at multiple test correction in this portion and how to do it with RStudio. So we know that multiple test correction is important because if we have a single study and we test for different group sizes, the pair of groups as we go along each time, and as we get more and more samples, we'll find some instances where we just happen to get small p-values as we go along, even though there's no actual difference when we have the most samples, which is what matters. So this multiple testing problem is something we have to consider when we test multiple data points more than once, test individual data points more than once. And we know that we went through the Benjamini-Hochberg method by hand in the introductory video. Think about how this interprets the ranks in your observed p-value distribution and compares them to expected values based on this formula where you have the rank multiplied by the alpha value of interest and the n, the number of samples that you take. So that means for each value, we might have 100 samples, 100 p-values, and alpha equals 0.05. Therefore, our first rank, rank 1, will have that corresponding value of 0.0005. And the next one, the expected value will be 0.00001, 0015, 0020, and so on. It'll iterate through those different options. We compare our observed value versus this expected value. So as an illustration here, if we have 100 trees with alpha value threshold the same as before, we can use that formula. So what we do is we sort our observed values. So we have some distribution ranging from 0 to 1 for our p-values, and we sort them in order. So you can think of them sorting them like we're just putting them in order as we collated them through our different tests that we did. We rank them. So we have ranks 1, 2, 3, 4, and so on. And then we compare each one individually. So we take the first one. So this is our observed p-value 0.0001. And the theoretical expected value we get is 0.0005. And that comes from this formula here, given these conditions. And we say that if this observed value is smaller than our threshold value, we say that yes, we do not accept the null hypothesis for this value. We can study that further. And then for the second one, if we have value 0.004 and the threshold value is 0.0010, we might say, yes, let's look at that further in the same way. And if a third one is 0.0022 and our threshold value is 0.0015, we might say, no, we accept the null hypothesis for that particular feature and skip the remainder. So skip all the other ones. We don't need to do any further testing. So the Benjamini-Hochberg approach is similar to this, where we're using the p.adjust function, which we can try now in RStudio. So in this case, we're looking at multiple test correction, and we're going to use this function p.adjust. We can get help on this function if we run this command on line 152 and find out more about the details about how this function works here. And what you can see there is there's a range of different methods that we can apply, and it takes on board a numeric vector of the p-values, so all the p-values you want to examine, the method, and then the number of comparisons, which is simply the length of p. And then there's an example at the bottom, but it's pretty easy to run. There's different multiple test correction methods listed on line 155, like Holm, Hochberg, Hummel, Bonferroni, Benjamini-Hochberg, BH, the false discovery rate, and so on. The ones in practice that we want to use are probably Benjamini-Hochberg, or the false discovery rate is another option too. So what we're going to do here is focus on the Benjamini-Hochberg method and generate a uniform distribution of p-values using this command on line 157. And what we can do is check the length of p-values. So you've got 1,000 numbers with this range of 0 to 0.2. So if we plot that next, we see we get a kind of uniform distribution. Of course, this is random. So if we repeat this process of drawing it, we'll see that we get random distributions every single time. And then we can take this function. So p.adjust takes on board this vector of p-values, the method, is p.adjust message 6, which is simply the Benjamini-Hochberg one. Oh, it isn't. It should be 5. Benjamini-Hochberg 5. And we can replace this with that in quotes, BH instead. And then our length of the p-values, the number of p-values at the end. So that will correct for 1,000 p-values using that method. So that generates our vector of the corrected p-values. So we can see that there. And what we can do is sort that vector. So if we sort that, we'll find that inevitably many of our p-values come close to our threshold for the initial distribution of 0.2 or 1 is what you'll see in practice. And you can see the ones that are smaller at the start. So if we look at the original p-value distribution we had, you can see this initial ones were much smaller. So what we can do is plot them against each other. So if we take this here, if we do a simple plot, we can see that shape. So what we're going to do is add in colors of red. We're going to limit the x and y axis because it's 0.2. Well, not for this plot actually. We'll just leave it as it is for visual clarity, and add a grid as well. So we look at the grid there. We can see how the observed p-values are quite different for the corrected p-values. So let's adjust the y limits, x and y limits. So you can see there that's a distribution shape. So let's zoom in back to this. So scaling the axis is important here because that might warp our perspective. So you can see there our observed p-value might be very small for the first one, but its actual corrected value is near 0.01. And the same for second one, it's very small for the observed value, but the actual corrected value is about 0.12, and so on. So this indicates that there's actually no effect here, which we'd expect because this vector is just random. So if we repeat this and repeat the correction and repeat this plot for a range of 0.2 to 0.2, we can see there, again, we got no difference. So what we can try then is create a vector where we add in a series of numbers that are very small p-values. So this kind of biases our analysis, and this may create an imaginary situation where maybe there are some effects. And we can look at that histogram, and we can see that there are some p-values that are quite small here in the first bunch. And we can correct those in the same way in line 173 using the p.adjust for Benjamini-Hochberg correction again. And then plot these in the same way in the color blue. So now we see we're going from the corrected ones are on the y-axis, the uncorrected ones are on the x-axis. So you can see now we actually have some that are small. So if we look at the first few of the sorted corrected p-values, you can see that some are still quite small. Whereas most of them are much, much larger. So in this case, we might actually have 20 or so that actually are extreme in this context. So here we see that the plot is different and that there may be real effects here for those, for that number. So you see there, if we look at the first 20 or 22, that the first 21 or so appear to have a difference that might be worth looking at further. Whereas in our original assessment where there was no real difference, they all have more large p-values. So this is one approach for multiple test correction. So you can use this code, and the way to do it is to create a vector, p-value vector, to which we add our p-values as we go through our analysis. So that could be something you think about. How many dependent tests have you done, where you look at the same data using multiple tests? And the way to do it is to take that p-value. So you might have some p-value called p-value 1, and let's give it some value. It's 0.123. If you want to create a p-value vector, call it p-value vector, it might have nothing at the start. So we're just going to use C and nothing inside that C function. That creates an empty vector with that name. And then we add our first p-value into that. So I'll take the original p-value vector name and add p-value 1 into there, like that. And then you might have another p-value we have. So let's say our next p-value we find, I get a p-value of 0.08. I add that in there, and now p-value vector now contains two values. So you have to remember the order in which we add them. So you might put comments as we go through our script and create our script and add these in there to make sure we track what p-values we have. And we keep going through this process and add our p-values in there as we conduct our different analysis. And that's all p-values, not just ones that were small or are of interest to us. We have to add all of them in there. And that will mean at the end, we get this p-value vector like this, and then we can correct that. So we can use the same code we had here. So we take this code down here. So we're going to take our p-value vector, plot it. So you can see there's not many entries. We're going to get our corrected version for the corrected length. I get the corrected values, and we're going to see what p-value correct has. So you can see now the corrected ones are there. And you can see the original values were here. So the value of 0.123 has been corrected to 0.172, 0.08 has been corrected to 0.16, 0.04 has been corrected to 0.14, 0.012 has been corrected to 0.08, and so on. So that means we can, if we write comments in our code to say where we're doing this, we can track our p-values as we go through our script and have our initial uncorrected p-values here below, and then have the corrected vector here at the end for our final reporting. So that can mean as you do new tests, you can still correct your p-values in an appropriate manner without having to repeat your collation of the different p-values. And you may have instances where you do a really big analysis. You may have 100 p-values for which you have to correct. And this will enable you to kind of track them as you go through your script, collate them, and then correct for them all together afterwards at the final stage, and not at the intermediate stage where you have to go back and repeat this process. So that can mean you have to just flag whether something's a raw p-value that's not corrected, and where something is a corrected p-value. Okay, so that's the end of this video.